Hello everyone, and welcome back to Math 220A Mathematical Logic, Lecture 20, Prime and Atomic Models. Today we will use the emitting type theorem from the previous lecture to study small models of a complete theory. Throughout this section, we will assume that L is a countable language, and we will assume that T, a complete L theory, with infinite models. Definition. We say that a model M of T is a prime model of T if for any n model of T there is an elementary embedding of M into n. Let's consider a couple of examples. One, assume that T is the theory of algebraically closed fields of characteristic 0 if K is a model of AC of 0, hence an algebraically closed field, and F is the algebraic closure of Q, the field of rational numbers, then there is an embedding of F into K, and since the theory of algebraically closed fields of characteristic 0 has quantifier elimination, it follows that this embedding is elementary. This shows that F is a prime model of AC of 0. Similarly, the theory of real closed fields, RCF, has a prime model, namely the real closure of Q, as we have already discussed in the lecture on the quantifier elimination in RCF. And for a third example, we consider the theory of the natural numbers in the language L consisting of addition, multiplication less than 0, 1. So then T is the theory of the true arithmetic. Now, if M is a model of T, then we can view the actual natural numbers n as an initial segment of M, namely because we have the constant symbols 0 and 1. Then we can consider the interpretation of the term 1 plus 1, 1 plus 1 plus 1, etc. This will give us an isomorphic copy of the natural numbers in M. Now we claim that this embedding is elementary. We can check it using the Tarski-Watt test. So namely, assume that phi of V W1 through Wm is an L formula and n1 through nm are natural numbers such that m satisfies exists v, phi of v and bar. So here we are viewing this as a tuple of elements from the corresponding copy of the natural numbers in M. Let psi be the L sentence, exists V, phi of V, 1 plus 1 plus 1, etc. and 1 times, etc. 1 plus 1 plus 1 plus 1, etc. and M times okay, so this gives us an L sentence. Then we have that M satisfies psi and also that the actual natural numbers satisfies psi because M is elementarily equivalent to N in our language L, because remember M is a model of the true arithmetic, the complete theory of the natural numbers. But then for some S in N, we have that N satisfies phi of S 1 plus 1 plus 1, etc. and 1 times through 1 plus 1 plus 1, etc. and M times, and we also have that the natural numbers satisfy phi of S, namely we take the term 1 plus 1 plus 1 plus 1 S times, and then the rest is the same, so 1 plus 1 plus 1 and 1 times through 1 plus 1 plus 1 plus 1 and M times. Now note that the letter is again an L sentence. So we have that M, which is elementary equivalent to N, satisfies phi of 1 plus 1 plus 1 plus 1 S times, and the rest is the same. So we have that M satisfies phi of S and 1 through Nm, where S is the corresponding element of the copy of N in M. Hence, by Tarski-Watt, we conclude that N, the actual natural numbers, is an elementary substructure of M. So this shows that N is a prime model of its theory. Related to prime models are the so-called atomic models. Definition: we say that M, a model of T, is atomic if the complete type of a bar in M is isolated for all tuples a bar in M. First, we observe that if M is a prime model of T, then M is atomic. Proof: let M realizing T be prime, and suppose that J from M to N is an elementary embedding then if a bar is a tuple of length n from M, and it realizes P and n type in T, then so does the image J of a bar, because the map J is elementary. But now, if P in SNT is non-isolated, by the meeting types theorem, there exists some n, a model of T, such that n omits P, it follows that if M realizes P, then we cannot elementarily embed M into N, which omits P. So it follows that M must omit P. In particular, if a bar is a tuple from M, then the type of a bar in M must be isolated. So we use that prime model can be elementarily embedded into any model, which forces all of its types to be isolated. For countable models, the converse is also true. Namely, we have the following theorem. Let L be a countable language, and let T be a complete L theory with infinite models. Then a model M of T is prime if and only if M is countable and atomic. Proof. The implication from left to right we have already seen in the previous proposition that prime models are atomic, but also as L is countable, T has a countable model, thus the prime model M must also be countable, because it can be elementarily embedded, so in particular embedded into a countable model. So it has to be countable itself. So now we prove the converse implication. Assume that M is countable and atomic, and let N be an arbitrary model of T, so we must construct an elementary embedding of M into N. Towards this purpose, let M0, M1, etc., Mn, etc., be an enumeration of M, which is countable, we're assuming. Now for each I, a natural number. We let theta I of x0 through xi isolate the type over the empty set of the tuple m0 through mi by the assumption of atomicity. The type of any tuple is isolated. So in particular, there is a formula like this. Now we will build f0 contained in f1, contained in f2, etc. a sequence of partial elementary maps from M into N such that the domain of the map Fi is precisely the elements M0 through Mi minus 1. Then, if we take F to be the union of these maps, we see that F is an elementary embedding of M into N. So the task is then now to build such functions. So we take F0 to be empty. Since we have that M is elementarily equivalent to N, we see that in particular F0 is partial elementary. For the inductive step, given Fs, we let Ni be the image of the element Mi under Fs for I less than S. So all of them are in the domain, so this is well defined. Now, as theta S of M0 through Ms holds in M, and the map Fs is partial elementary, we have that N also satisfies exists V theta S of N0 through Ns minus 1 V. Note that the only parameters here are N0 through Ns minus 1, so they are all in the domain of S, which is partial elementary, so it preserves the truth value of this formula. Now we let Ns in N be such that it witness this existential quantifier. So N satisfies theta S of N0 through Ns minus 1 Ns. As by assumption, theta S isolates the type of M0 through Ms over the empty set. It follows that the complete type of M0 through Ms in M is equal to the complete type of N0 through Ns in M. Thus, we can take Fs plus 1 to be Fs together with the pair Ms Ns, and this gives us a partial elementary map. So that its domain now contains the element Ms and concludes the proof of the inductive step, and hence of the theorem. this theorem will lead to a useful criterion for the existence of prime models of a given theory T. But before we can establish that criterion, we need an auxiliary lemma. Suppose that A is a subset of M and the tuple A bar B bar, where A is of length M and B bar is of length N, realizes an isolated type in S M plus N of A in M, then the type of A bar over A is also isolated. So a subtuple of a type with an isolated type itself has isolated type. Proof: let phi of x bar y bar isolate the type of the tuple A bar concatenated with B bar over A. We claim that then the formula exists y bar phi of x bar y bar isolates the type of A bar over A. To see this, let psi of x bar be any LA formula such that M satisfies psi of A bar. We must show that the A theory of M has as a logical consequence that exists y bar phi of x bar y bar implies psi of x bar. Note here that y doesn't occur in psi, so we can take it out of the brackets like this. So suppose not, then there is some tuple C bar in M of length M such that M satisfies exists y bar phi of C bar y bar and not psi of C bar. Let D bar in Mn be such that M satisfies phi of C bar D bar and the negation of psi C bar. By assumption, phi of x bar y bar isolates the type of A bar B bar over A. So we have then that the A theory of M implies phi of x bar y bar implies psi of x bar, but this is a contradiction because we have that psi of x bar belongs to the type of A bar over A, which is contained in the type of A bar B bar over A as a set of formulas. In particular, this tells us that if A bar B bar in M to the power M plus N realizes an isolated type in S M plus N of T, so a type without any parameters, then A bar realizes an isolated type in Sm of t. So this is just a special case of the lemma with A, the set of parameters capital A, taken to be the empty set. Now, with this lemma in hand, we can prove the main result of today's lecture, a characterization of those theories which admit prime models. Let L be a countable language, and let T be a complete L theory with infinite models, then the following are equivalent. 1. T has a prime model. 2. T has an atomic model. And 3. The isolated types in SNT are dense in the sense of the topology on the space of types for all n natural numbers. So the condition 3 gives us a topological criterion for the existence of atomic models and prime models. Proof. We have already shown that 1 is equivalent to 2. We show that 2 implies 3. To prove that the set of isolated types in Sn of t is dense, we must show that every open set, which is non-empty, contains a point, an isolated point. Since the topology is, so all open sets in our topology are just union of the basic open sets, we must show the following. Assume that phi of x bar is an L formula such that the corresponding basic open set in the topology is non-empty. Then we want to show that this basic open set, square brackets phi, contains an isolated type. So this is what we want to show. Towards this purpose, let M be an atomic model of T. As T is complete, and T, together with the formula phi of x bar, is consistent, since we're assuming that the set is non-empty, so the corresponding formula is consistent with T, we have, by completeness of the theory T, that T implies exists x bar phi of x bar. Thus, there is a tuple, a bar, in M to the n, such that M satisfies phi of a bar, but then the complete type of a bar is an element of the corresponding open set square brackets phi, and as M is atomic, we have that the type of a bar is isolated. So we have shown that every open set contains an isolated type. So this shows that the isolated types are dense. and so 3 holds. Our remaining task is then to show that 3 implies 2. So we suppose that the isolated types in T are dense, and we are going to build an atomic model of T via a Henkin argument as usual. We let C, consisting of C0, C1, etc., be a new set of constant symbols and we let L star be the language L together with these new constant symbols not in L. Let phi 0, phi 1, etc. list all L star sentences. Now we will build theta 0, theta 1, etc. a sequence of L star sentences such that if we take T star to be the theory consisting of all these sentences, theta I in N, together with T, then this is going to be a complete consistent theory with Henkin witnesses in C. And we will do it in such a way that the canonical model of T star, namely the model with the base set given by the interpretations of the constant symbols in C, is atomic. So that the canonical model of T star is atomic. For the construction, we assume inductively that T together with theta S is consistent and that theta S plus 1 implies theta S. So every next sentence is going to imply the previous one. Again, there are 3 properties that we want to arrange infinitely often. So for the stage 0 of the construction, we can take theta 0 to be the sentence exists x, x equals x. Now for the stage s plus 1 of the form 3i plus 1 for some I, in this, on these steps we're going to assure completeness of the resulting theory. If we have that T together with theta S conjunction phi I is satisfiable, we can let theta S plus 1 be theta S conjunction with phi I, and if it is not satisfiable, we let theta S plus 1 be theta S conjunction with the negation of phi I, This clause will ensure that every sentence or its negation will be implied by the theory T star that we were constructing. Now for the stage s plus 1 of the form 3i plus 2 for some I. In this case, we ensure existence of Henkin witnesses in C. If phi I is of the form exists x psi of x for some psi of x and L formula, and theta s implies phi I, we let C in C be a constant symbol not occurring in theta s. As usual, theta s is a single sentence, so can only contain finitely many constant symbols from C, and we can pick one which does not appear in it. And we let theta s plus 1 be the conjunction of theta s and psi of C. Otherwise, if phi I is not of the required form, or theta s doesn't imply phi I, we let theta s plus 1 to be simply theta s. As in the proof of the Hermitian types theorem, we can see that T together with theta s plus 1 is consistent. Now, the remaining stage is the case when s plus 1 is of the form 3i plus 3 for some I. On this stage, we let n be minimal, such that all of the constants in C that occur in theta s are from the list C0 through Cn. It has to exist, because theta s contains only finitely many constant symbols from C. And we let psi of x0 through xn be an L formula such that theta s is equal to psi of C0 through Cn. Then we clearly have that T together with psi of x0 through xn is satisfiable, because by the inductive assumption T with theta s is satisfiable. Now, since the isolated types in SNT are dense, and we assumed satisfiability of psi, which means that the corresponding basic Klopen set, square brackets psi, is non-empty. So by density of the isolated types, there must exist an isolated type P belonging to this basic Klopen set, square brackets psi. Since P is isolated, we can let chi of x bar be some L formula isolating P. In particular, we have that the basic Klopen set given by chi consists of a single point P and T together with chi of x bar is satisfiable. Then we let theta s plus 1 be the sentence chi of C bar. Then T together with theta s plus 1 is satisfiable. And we also have that because psi of x bar is in P and chi isolates P, we have that theta s plus 1 implies theta s as required. This concludes the construction, the inductive step of the construction. Now, as in the proof of the emitting types theorem, we conclude that the theory T star obtained by T together with all these sentences, theta 0, theta 1, etc., is a complete theory with Henkin witnesses in C. Then we can take M, the canonical model of T star, so such that the base set of M consists of the interpretations of the constant symbols C and C. We claim that M is atomic, or more precisely, the L reduct of M is atomic. To prove this claim, let d bar, let's say consisting of d1 through dm, in m to the n be an arbitrary tuple. So in fact, we're interested in the interpretation of the corresponding constant symbols in M. So in M, by assumption, every element is an interpretation of a constant symbol. So an arbitrary tuple can be presented as a tuple of interpretations of some constant symbols. Now, by construction, we can find natural number n and an s of the form 3i plus 2, such that each constant symbol di is in the set C0 through Cn, and n is minimal, such that C0 through Cn contains all constant symbols in C occurring in theta s. Now, by construction again, at stage s plus 1, we make sure that the tuple given by the interpretations of these constant symbols in M, so C0 M through Cn M, realizes an isolated type Note that the tuple D might be a proper subtuple of the tuple C bar, but we already proved in the previous lemma that any subtuple of a tuple realizing an isolated type itself has isolated type. So by the lemma, we have that d bar m also realizes an isolated type. And since d bar m was an arbitrary tuple in the model M, we have proved that types of all tuples in M are isolated, which means that M is atomic, and concludes the proof of the theory. Finally, let us stress that not all theories have prime models, and we give a sketch of an example demonstrating it. Let L be the language with unary predicates PS of X for every 0,1 sequence S of finite length, then the axioms of L theory 3 will say the following. So we want to express that the predicates PS for S a finite sequence of zeros and ones form a binary decomposition of the universe. So namely, we will have for every X P empty set of X holds, so this is the whole universe, exists X PS of X, so every predicate is non-empty. For all X, we have that PS with 0 added at the end of X, or PS with 1 added at the end. So they split the universe into two if we add 0 or 1, and also they cover PS of X. So each predicate PS gets split into two parts corresponding to the extension of the sequence S by 0 and by 1. And finally, for all X, we have not PS0 of X and PS1 of X. So all the predicates corresponding to continuation of a sequence S by 0 and by 1 are disjoint. We claim that the theory 3 has quantifier elimination and is complete. We leave verification of this claim as an exercise, and once we have quantifier elimination, we can then conclude that there are no isolated types in 3. We also leave verification of this as an exercise. The reason being that no matter what formula we pick without quantifiers in this language, it cannot isolate a type because we can also pick two types, one of them containing PS0, the other one containing PS1 for an appropriate S. But then by the theorem we just proved, if there are no isolated types, they certainly cannot be dense. So it implies that there are no prime models of this theory.